Light takes on multiple forms, so let's define and describe its energy accordingly. Broadly speaking, energy is the ability or capacity of a system to do work and to make change happen. It takes many different forms, such as chemical energy and electrical energy, and it's described in different ways accordingly, but overall, we classify all types of energy as a combination of kinetic, energy of motion, and potential, energy of position or state. Light is simultaneously a wave, a propagating disturbance of energy transfer, and a particle, a discrete pocket of energy capable of interacting with matter. We refer to the wave form of light as electromagnetic radiation, whereas the particle form is called photon. EMR and photons are both light in the same way that we are simultaneously a mind and a body. They're inseparable, as our mind doesn't exist without our body and vice versa. Likewise, electromagnetic radiation propagates through space as waves, carrying energy from one place to another. This energy is quantized into discrete packets known as photons. Therefore, photons are EMR and EMR is photons. So we can understand light energy based on the way it interacts with things. One, in its movement through space creating field disturbances, and more tangibly in its interaction with matter such as electrons through absorption, emission, excitation, etc. After all, energy is the ability to do work and to make change happen. Here we see the most prominent equations which describe each respective light form. For waves, it's solving for propagation or travel speed. For particles, it's quantifying the energy. While both EMR and photons have energy, they both are energy. We're usually more concerned about putting a number to that energy when describing light as a particle, a photon. I mentioned earlier that any type of energy can be broken down into a combination of kinetic and potential energy. The waveform of light carries energy associated with its motion through space. C is travel speed after all. As EMR waves propagate, they transfer energy from one location to another. The photon manifests potential energy, because when a particle of light interacts with matter, it can transfer its energy, leading to changes in the energy state of that matter, such as exciting electrons to higher energy levels. It's a measure of how much change it has the potential of inducing in other matter it interacts with. So anytime you need to calculate light energy, this is the main equation you want to use. Energy of the photon equals the product of h and frequency of the photon. H is what's called Planck's constant, and it's equal to 6.626 times 10 to the negative 34 joule seconds. These are the units of each respective variable, and as you can see, energy is measured in joules. Each joule is 1 gram meter per second squared. Even though there are an infinite number of energy values light can be, as witnessed by this continuous line, light energy is described as being in discrete pockets of photons, because for any given energy, there is one and only one corresponding energy that that photon can have. In other words, any one photon cannot change the amount of energy it has. These two terms are what's called directly proportional, meaning that when one term increases, so does the other, and when one term decreases, so does the other. Furthermore, this line modeling this direct relationship has a constant slope equal to Planck's constant. In the context of solving light energy problems, we are very often going to be given the wavelength and asked to find the energy. But hold on a second. Wavelength is nowhere to be found in our equation for calculating energy. Here's where our understanding of light's dual nature comes into play. While this equation on the left is used to describe light's wave behavior, because EMR and photons are one and the same, we can nonetheless borrow the equation from a variable standpoint. And we can see that both equations have a frequency term. This means that we can combine both equations to derive a new equation that relates the energy of the photon with the wavelength. As opposed to the direct relationship between energy and frequency, wavelength is inversely proportional to energy, meaning that when one of these two terms increases, the other decreases, and vice versa. So did you learn the following? 1. Energy is the ability to do work and make change happen. It comes in many different forms, and any form is ultimately a combination of kinetic and potential. 2. Light is simultaneously a wave and a particle of energy. We use both forms of light to describe light's energy. Likewise, we quantify the energy of photons using these two equations.